Big concerns this morning in Florida where a massive sinkhole opened up, draining radioactive water into an underground water source.
Florida's ocean floor is collapsing in ways scientists never expected. In late 2024, NOAA vessels mapping the Florida Straits found massive sinkholes forming in real time, some wider than football fields and deeper than skyscrapers. These aren't stable scars of the past. They're active, expanding voids that could reshape the seafloor. What's driving them? Methane eruptions, brine pockets, or hidden aquifer collapses? And how close are these hazards to shipping lanes and coral reefs? Today, we'll uncover the forces tearing Florida's ocean floor apart and what it means for the coast. Active collapses mapped. When scientists first announced that sudden depressions had been found forming off Florida's coast, the news sounded almost unbelievable. Yet, sonar mapping from NOAA expeditions left no room for doubt. Vast, circular pits had appeared on the seafloor, some measuring hundreds of feet across, large enough to swallow entire city blocks if they were on land. These are not the exaggerated giant holes of urban legend or movie plots, but they are no less alarming. They represent active, fast-forming seafloor sinkholes, depressions carved into sediment layers that were thought to be stable. The scale of these collapses is staggering, with depths equivalent to 30-story buildings and diameters rivaling major stadiums. To oceanographers accustomed to slow geologic change, the suddenness of these features is what makes them so unsettling. Sonar images reveal details that deepen the mystery. Inside the sinkholes, swirling sediment plumes spiral upward like underwater smoke, evidence of material collapsing into the voids below. Chemical sensors mounted on underwater drones show abrupt shifts in water chemistry, changes in oxygen levels, pH, and even methane concentrations, all within a few feet of the depression's rims. These signs point to a rapid process of sediment failure, not the slow rolling dune migration or erosion typically seen on the seabed. In fact, the turbulent flows resemble the behavior of Florida's famous blue holes, deep vertical shafts in limestone that extend far below the seafloor. By comparing the data from these new collapses with older blue hole studies, researchers confirm that they are looking at a very real hazard and not just another natural quirk of the ocean floor. The combination of spiraling sediments and chemical anomalies suggests powerful forces are acting beneath the surface, destabilizing material that should otherwise be locked in place. Equally concerning is where these collapse zones are appearing. Some lie dangerously close to Florida's coral reef tracts, ecosystems already fighting for survival due to bleaching, rising temperatures, and pollution. A sudden slump of sediment or collapse plume could blanket fragile reefs in suffocating clouds of debris, hastening their decline. Others are located near heavily trafficked shipping lanes, places where massive cruise liners, container ships, and fishing vessels pass daily. A large sinkhole opening beneath these routes could stir currents strong enough to disrupt navigation, while exposed edges may pose a threat to anchors and submersibles. Remotely operated vehicles, ROVs, which often investigate these sites, risk being damaged or even pulled into unstable sediments. For marine infrastructure, cables, or pipelines laid along the seafloor, such collapses could prove catastrophic. Scientists emphasize that these are not isolated events. The clustering of sinkholes in certain regions points toward a larger, systemic process at work. Some pits even appear aligned along invisible lines, as though connected by hidden pathways or underground tunnels within the seafloor. That possibility raises urgent questions. If these collapses are linked by subterranean channels, then one failure could trigger another, creating a chain reaction across the continental shelf. What might look like a single depression today could actually be the surface expression of a much bigger and more dangerous plumbing system beneath Florida's ocean floor. The pattern hints at underground plumbing, channels and cavities linking one collapse to another. So what exactly is tunneling beneath Florida's seabed? Hidden plumbing, real triggers. Florida's geology has always made it vulnerable to collapse. On land, the state is famous for sinkholes that suddenly swallow homes, parking lots, and even entire streets. The culprit is karst, porous limestone that dissolves over time as slightly acidic groundwater seeps through it, carving out hidden cavities. Eventually, the roof of these cavities weakens, giving way with little warning. This process has been well documented inland, but researchers are increasingly convinced that the same dynamics are unfolding offshore. The Florida platform extends far beneath the water, made of the same carbonate layers riddled with weak zones. With ocean circulation, salinity fluctuations, and pressure from tides and storms, the conditions for dissolution and collapse may be even more extreme than on land. In other words, the ocean floor near Florida may be subject to the same geological fragility that makes the state notorious for sinkholes on the surface. Evidence suggests that these offshore voids aren't isolated. Instead, they could be connected by vast subterranean channels, natural plumbing systems that snake beneath the seabed. Just as underground rivers link Florida's inland springs and sinkholes, similar conduits may run beneath the continental shelf. If one roof section begins to thin due to chemical erosion or sediment flushing, the stress can transfer to neighboring sections. A localized slump may then cascade downslope, triggering multiple collapses in quick succession. This kind of domino effect explains why clusters of sinkholes appear in specific areas rather than being scattered randomly across the seafloor. It also raises the alarming possibility that one failure could set off a chain reaction, spreading instability across an entire region of the continental margin. Adding to the natural risks are the pressures of modern life. Florida's groundwater has been heavily tapped for agriculture, urban growth, and industry. When aquifers lose water, the pressure balance changes, sometimes leading to void formation or collapse far from the pumping site. Onshore, this can cause sudden sinkholes under neighborhoods. Offshore, it could mean unseen changes in pore pressures that travel through aquifer pathways and destabilize sediments beneath the seafloor. Extreme weather conditions aggravate the situation. Storms push strong pressure waves into coastal aquifers, while heavy rain brings on sediment loads, further weighing down already delicate strata. On the other hand, droughts draw water tables down, breaking the fragile equilibrium that prevents cavities from collapsing. By themselves, each of these stressors may not trigger a collapse, but together they might tilt the system towards failure. Offshore detection of these threats is fraught with difficulty. On land, there are clear indications: cracks in driveways, leaning fence posts, and sudden water losses from swimming pools. The underwater equivalents of these would be subtle: micro cracks in sediment layers, gradual irregular tilting of the seabed, or unexplained seepage detected by ROV sensors. Scientists are trying to get ahead of the calamity by making monitoring technologies better at picking up these early warning signals. They are pondering a kind of monitoring that would include using seafloor tilt meters, pore pressure gauges, and chemical probes in concert to catch a collapse before it happens. However, the ocean is too big, and most of Florida's beneath-the-sea plumbing remains invisible. But cavities don't collapse without energy, so what's driving the punch that makes the sea floor give way? Pressure, gas, and lava, potholes. If Florida's offshore plumbing system provides the cavities, then pressure is the force that turns them from hidden voids into catastrophic collapses. One of the key culprits is methane hydrate, a strange ice-like compound that traps methane gas molecules inside cages of frozen water. These hydrates remain stable under cold, high-pressure conditions at the seabed, but when ocean temperatures rise or when sediment pressure shifts, the hydrates destabilize, releasing gas into surrounding layers. As methane expands and rises, it can fluidize the sediment above, prying open weak layers and forcing cracks to widen. Imagine the seafloor being lifted from below like a car jack, then suddenly dropping when the gas pocket vents. The collapse is not gradual, it is violent and fast, leaving behind the yawning pits researchers now call oceanic sinkholes. The threat doesn't stop with methane. Brine pockets, highly saline water trapped deep underground, can also exert destabilizing force. When these brines shift, they alter buoyancy and pressure balances within the seabed. Combined with rising gas columns, they create zones where sediment is no longer strong enough to hold itself together. This dynamic mirrors processes scientists have observed elsewhere in the world's oceans, where pressurized fluids suddenly vent, carving craters and channels into the seabed. For Florida, the danger is magnified by the fact that these processes are happening in a region bordered by coral reefs, heavy shipping traffic, and densely populated coastlines. To understand how such pits form, researchers often look to analogues from other parts of the world. One striking example comes from work led by University of Florida geologists on collapsed lava bubbles along the mid-ocean ridge in the Pacific. There, scientists discovered semicircular pits and jagged depressions caused not by erosion, but by vapor trapped beneath lava flows. Because molten rock spread over the ocean floor, seawater that was trapped below vaporized into the bubbles' inflation, which buoyed the lava sheets. Those bubbles, under the extreme pressure, crushed very quickly, leaving hardened potholes behind. Florida's continental margin is not a volcanic one, yet the physics are strikingly similar. Fluids are trapped under a roof, pressure builds, buoyancy lifts the roof, and voila! Quick implosion shapes the void. The analogy goes that such pressure and vapor brine interactions might be responsible for shaping the seafloor of Florida in ways that scientists are just beginning to map. Florida has its sinkholes on land. From that different angle, dominated in three types onshore: solution sinkholes, in which limestone slowly dissolves; subsidence sinkholes, in which thin soil masses slump into cavities; and collapse sinkholes, the deadliest, which come up suddenly when the ceiling of a cavity collapses. These are also true for offshore, but conditions there are more stringent. Deeper pressures, saline chemistry, and sloped terrain mean that a small void can grow into a major collapse much faster than its counterparts on land. The warning signs on land, driveway cracks, leaning trees, or sudden water loss, translate into the underwater world as micro cracks in sediments, unexplained tilting of seabed structures, or sudden plumes of gas and brine detected by ROVs and seabed gauges. The parallels between land and sea reinforce one troubling truth: the processes reshaping Florida's coast are not exotic. They are extensions of familiar hazards, now playing out beneath the waves with amplified force. If that energy focuses near the shelf edge, what happens when a section lets go all at once? Shelf slumps and wave threat. If sinkholes and cavities are unsettling on their own, the real danger emerges when they occur near Florida's continental shelf edge. The Florida Escarpment and the Miami Terrace are two massive underwater features that mark abrupt changes in depth. These zones are naturally unstable, long slopes of sediment perched above deeper basins. Under ordinary circumstances, they creep downward by a few centimeters each year, barely noticeable on human timescales. But add weakening sediment, methane gas pockets, and shifting brine layers, and those gradual movements can reach a tipping point. When enough stress builds along a failure plane, the slope can suddenly slump, sending entire sections of seabed crashing downslope in a matter of minutes. What begins as a quiet creep can end as an underwater landslide on a colossal scale. The consequences of such a slump extend far beyond the seafloor. When large masses of sediment rapidly shift, they displace massive volumes of water above them. The result is a pulse of energy that propagates as a wave. Unlike tsunamis generated by distant earthquakes, which may take hours to cross oceans, these waves would hit Florida's coast almost immediately. Modeling studies show that in some scenarios, slide-driven waves could reach shore within an hour, and in extreme cases, just minutes. Most of these waves would be modest, rising a few feet above normal sea levels. But in low-lying neighborhoods or narrow inlets, even a small surge could cause flooding, erosion, and significant property damage. In a worst-case slump event, with large amounts of sediment released at once, wave heights could surge into the double digits. For a state where millions live at or near sea level, the implications are sobering. Evidence suggests these scenarios are not just hypothetical. Ancient deposits pulled from sediment cores along the Atlantic coast reveal signs of massive waves reaching Florida's shores in the distant past. These layers contain coarse sand, broken shells, and marine debris buried deep within marsh sediments far inland, markers consistent with tsunami-like flooding. Some of the layers date back thousands of years, while others may be only a few centuries old. Their presence challenges the long-held belief that Florida is largely safe from tsunami hazards. If waves this powerful have struck before, they can strike again. And with modern development sprawling across the coast, the potential impact is far greater today. Scientists are working to close the gap between theory and preparedness. Early warning systems are now a top priority. Networks of seafloor pressure recorders, acoustic arrays, and tilt meters are being deployed to detect the first signs of instability. These instruments are designed to pick up subtle precursors, tiny tremors, sudden pressure drops, or acoustic pings from shifting sediments that may foreshadow a larger slide. But there are challenges. The continental shelf is vast, and the number of sensors needed to cover it adequately is enormous. Data must also be processed in real time to provide alerts fast enough to matter. Even a 30-minute warning could make the difference between safe evacuation and disaster for coastal communities. Florida has always lived with the risks of hurricanes and storm surge, but the possibility of wave threats from below the ocean adds a new and unsettling layer. If a sudden slump occurs at the shelf edge, the state could find itself facing a disaster without the usual meteorological warnings. So how do we move from alarming theory to practical protection before the next sudden collapse? Monitoring, mitigation, action. Florida's offshore story doesn't have to end in unchecked collapse. Scientists are building an arsenal of tools to keep pace with the seafloor's shifting moods. Multi-beam sonar mapping provides detailed snapshots of the ocean floor, revealing new pits as soon as they appear. Repeat bathymetric surveys layer these snapshots over time, making changes visible like frames in a stop-motion film. Bottom pressure recorders detect subtle micro-slumps, while hydrophones pick up eerie low-frequency drumbeats that may signal sediment shifts or rising gas plumes. Chemistry probes measure changes in methane or brine concentrations, identifying sites where instability is building. Combined, these instruments offer a kind of nowcast for seafloor stability, a living picture of where stresses are mounting and where collapses are most likely to erupt next. But technology alone isn't enough. Lessons from Florida's land-based sinkholes are being applied in surprising ways. Onshore, engineers use void filling and compaction grouting to stabilize collapsing ground beneath homes and roads. While no one is going to inject foam under the Gulf Stream, the underlying principle, reinforcing vulnerable zones and diverting critical infrastructure, can carry offshore. Fiber optic cables and oil pipelines, for instance, can be rerouted away from active sinkhole clusters. Where rerouting isn't possible, segments can be armored or suspended across high-risk gaps to prevent damage if the ground beneath suddenly drops. Even shipping lanes may one day be adjusted with standoff zones, creating safe margins around collapse-prone areas to protect vessels, anchors, and remotely operated vehicles. The ocean floor may not be repairable in the same way a suburban street is, but infrastructure can be adapted to survive its instability. Another lesson comes from unexpected places, the study of collapsed lava bubbles. University of Florida geologists showed that vapor trapped beneath lava sheets can buoy up rock layers before imploding, leaving behind pothole-like depressions. That analogy is now inspiring new approaches offshore. By sampling material beneath hardened crusts near Florida's sinkholes, scientists can search for telltale drip features, mineral signatures, and porosity patterns. These details reveal whether a pit is old and stable, still pressurized, or primed for collapse. In effect, the seafloor can be triaged. Sites can be labeled as dormant, active, or hazardous. Such classifications are critical for prioritizing which zones demand sensors, which should be avoided by infrastructure projects, and which can be studied more safely. The challenge is scale. Florida's continental margin is vast, and resources are finite. Mapping every inch is impossible. Instead, scientists are developing risk models that highlight the most vulnerable areas where karst geology, methane seeps, and shelf slopes overlap. These models guide the placement of sensors and inform emergency planning for coastal communities. At the same time, public awareness must grow. Just as Floridians on land learn to spot warning signs of sinkholes, cracks in walls, slanting trees, or sudden water loss, coastal residents need to understand the offshore equivalents. They may never see the cracks forming beneath the sea, but knowing that collapses can generate waves or turbidity events is vital for preparedness. Florida's future will depend on balancing vigilance with adaptation. The ocean floor is not static. It is alive with forces of dissolution, pressure, and collapse. Monitoring and mitigation strategies can buy time, but they cannot eliminate the hazard. The best defense is staying ahead of the changes, acknowledging the risks, and planning for a coastline that must coexist with a restless seafloor. Besides, little did we appreciate that the greatest risk may rise also from the gaps between what can be measured today and how fast the seafloor is changing tomorrow. Those blind spots leave scientists working against the clock, trying to predict collapses before they occur, rather than trying to work out what really happened after the damage is done. And in a vulnerable state such as Florida, that foresight or hindsight could mean the difference between a community keeping itself safe or facing the ocean's sudden wrath. If Florida's offshore sinkholes are growing, the time to act is now. Like, comment, and subscribe if you want more clear, grounded reporting on coastal risks. Tell us which factor worries you most: gas releases, karst channels, or shelf edge slumps, and watch the next video on screen to see how ocean sensors are rewriting hazard maps in real time.